And depending on our density conditions, density regimes, we will have different of these heating processes being dominant. So looking at the warm neutral medium, so densities below maybe 1 particle per cubic centimeter, we will have at the very low density regime mostly cosmic ray and X-ray heating being most efficient, but then photoelectric heating as a process with a stronger density dependence taking over at some point. So these lines here basically have a density independent behavior. That's why they have here this actual constant incline here. The densities are so low that the photoelectric heating, for example, contribution of the ionization of atomic carbon or so is yet too inefficient to actually contribute, and turbulence heating due to the low density will also only marginally contribute here. When we move to the denser regimes, so we extend the plot on the right hand side, here's the density, and move into the diffuse cloud regimes, we already saw that the photoelectric heating is now more efficient than the cosmic rays. This is shown here, and at some point the density behavior becomes somewhat less steep, and this will then allow to take over at higher densities, for example of other processes. We see that the ionization of atomic carbon is now becoming much more important as the density increases. And in the molecular cloud regime, we will then have other processes also being important. The photoelectric heating here is not shown because we now assume that we are shielding the UV radiation, but cosmic rays can still penetrate. And we have gas and dust heating slowly becoming more and more important the denser the gas becomes. So we see that depending on the actual physical environment, the interplay between the different heating processes changes. So summarizing, we saw that when we were looking at the different heating, that mostly they are the actual heating rate, the specific heating rate per particle is more or less independent of the density and the temperature. The cosmic ray interaction does not depend on the actual density of the gas or the temperature of the actual gas particles. The UV radiation is also ionizing the hydrogen gas or the carbon dust independent of the actual gas temperature. And this is of course also due to the fact that the energies involved are so different that they make little difference. So we saw that ionization is in the regime of maybe 10 electron volts, dust photoelectric heating in a regime of 5 to maybe 11 electron volt. Photodissociation is also in the same electron volt regime, and that the surplus energy then is used to kinetic gas heating. So the kinetic energy, typical energies are 0.1 to 0.7 kb times the effective UV temperature. so that typical energies that are then available to heat the gas by these different processes, converting them to Kelvin, are in the regimes of millions of Kelvin compared to temperatures of tens or hundreds of Kelvin. So even though our heating depends on the environment, the details of the heating rate are mostly independent of local densities and temperatures. So, and all these heating processes then later add up so that the total heating per molecule is a more constant number independent of the heating and cooling.